Welcome back. In this video, we're going to give a quick overview of planes in space and work a couple of examples of finding equations for a plane. So let's just first start with what the equation for a plane actually is, just in general. So a plane is given by a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. Or an alternative way to express this is to say that a times x plus b times y plus c times z has to be equal to d, where d is equal to ax naught plus by naught plus c z naught. And this a, b, and c, and then the x naught, y naught, and z naught come from the normal vector. That's what gives us a, b, and c. And then x naught, y naught, and z naught come from a known point P on our plane. So what that might look like, for example, if we wanted to sketch a plane like so, we would want to know what a vector normal to this plane looked like. That's n. And then we just simply need to know a point that's actually on the plane. And then every other point on this plane can be described by what fits into one of these two equations. So let's work an example. In our first example, we are going to find the equation for the plane that passes through P equal to 1, 2, 3. That's our point. And then has the normal vector n equal to 6, 7, 8. Okay. So I always like to start with whatever equation that is that we want to plug things into. So we start with that equation ax minus x naught plus b times y minus y naught plus c times z minus z naught. That's equal to 0. And the reason that we start with this equation as opposed to the other one is because it shows us each one of these pieces that we're looking for, the a, b, c, and the x naught, y naught, and z naught, as opposed to the other one, which kind of has a tendency to already have them all lumped together. So in this case, like I said, n is what gives us a, b, and c. And our point is what gives us the x naught, y naught, and z naught. So we're given n. That's the 6, 7, 8. So these are going to go in for a, b, and c. And we're told that p is equal to 1, 2, 3. So those are going to go in for the x naught, y naught, and z naught. So what we get for our equation then is going to be 6 times x minus 1 plus 7 times y minus 2 plus 8 times z minus 3. And then all of that's equal to 0. We can rearrange this a little bit to get that other format if you want. So we get 6x plus 7y plus 8z is equal to 6 times 1 plus 7 times 2 plus 8 times 3. Simplifying that down, 6x plus 7y plus 8z is equal to 44. So either of these two equations are our equation for this plane that passes through the point P equal to 1, 2, 3 and has normal vector 6, 7, 8. So this one was fairly straightforward because we're actually already given the normal vector and the desired point. Let's look at an example that maybe we have to dig a little bit for that kind of information. In this example, we are going to find the equation for the plane that contains 3 points, P equal to 1, 2, 3, Q equals 0, 1, 0, and R equals 0, 0, negative 2. Okay, so 3 points is definitely enough to be able to define a plane. That might be something that you've heard in like a high school geometry class or something. But the question is, how do we take this information and arrange it into something that's actually helpful for us? Well, first and foremost, we're starting with our equation. That A times x minus x naught plus B times y minus y naught plus C times z minus z naught. That's equal to 0. And this comes from that normal vector, A, B, C, and then some known point, P, that we want to have on our plane. Well, the point P isn't a problem because we have 3 points that we know we want to be on the plane. So any one of those 3 can fill this role right here. But so the sticky point here is going to be getting that normal vector. And the way that we are going to do that, I'm going to do this by sketching a picture just to kind of show what's going on here, is on this plane, we have the points. We know we want P, Q, and R. And from these points, we are able to define 2 vectors. For example, PQ and PR. And if we take their cross product, we will get something that is perpendicular to our plane. So that's exactly what we're going to do. We're going to take PQ cross PR to be our normal vector. So PQ is equal to -1, -1, -3. PR is equal to -1, -2, -5. And taking their cross product, we'll stack the I hat, J hat, K hat into the determinant bars and then put the vectors in the rows. Taking this determinant here, you're going to get -I hat minus 2J hat plus K hat. If this is a process that you're not necessarily super comfortable with, I would recommend that you go back and look at my cross product video. But what this means here is that our normal vector is equal to -1, -2, and 1. And we can choose any one of these 3 points that would serve as one of the points on the plane. I'm just going to go ahead and take P to be equal to 1, 2, 3. So taking these pieces and plugging it into this equation up here, we're going to get -1 times x minus 1 minus 2 times y minus 2, and then plus 1 times z minus 3 is all equal to 0. And if we want, we can rearrange this, moving all of our constant terms over to the right and leaving anything that has a variable on the left, and we get -x minus 2y plus z is equal to -2. And that's pretty much it for that example right there. Again, the big idea here was to just take these 3 points that we knew to be contained in the plane, use them to create the 2 vectors that we know to lie in the plane, and then use those 2 vectors to produce something that is perpendicular to the plane. And we do that by getting the cross product and then plugging all the values in that we already know. So that's it for this video. In another video, I'm going to go over a few more slightly involved examples of working with planes. So I'll see you next time.